Thank you, Jules. So I'm Eric. I'm a software engineer at Databricks, and I'm here to tell you today about robust and scalable ETL over cloud storage. So what is ETL? Well, it turns out it's actually the most common Spark use case. It stands for Extract, Transform, and Load, which covers a broad range of Spark workloads. So kind of in this example, we're extracting some data from storage, here a distributed file system. Spark applies some transformation to it, and finally it writes it back out to the same or maybe some different storage system. So to give you an example of what this looks like in code, here we have a simple example of ETL. We use spark.read.csv to read CSV files from some source in S3. We apply some aggregations to it. And finally, we write it back to S3 in a different location, this time in Parquet format. So ETL jobs are commonly chained together. This means that the output of one job might be the input of another. This means that reliable output is critical. With chained ETL jobs, the output of each job should be all or nothing. That is, the job should be committed atomically. Otherwise, the failure of one job can corrupt the input data of a downstream job. So the way Spark guarantees reliable output is via a commit protocol. So during the running of the job, Spark will stage the output files to a temporary location. Once the job completes successfully, Spark will then attempt to commit the outputs by moving the staged files to the final locations. If the job fails, Spark can just delete those temporary files. So an important part of this commit protocol is like actually moving the files to their final locations. HDFS, which is Hadoop's distributed file system, supports atomic metadata operations. So this allows like the staged file or maybe directory to be moved to its final location in just one metadata operation. So Spark's default commit protocol is the Hadoop MapReduce commit protocol, and that protocol uses one or a series of file moves for job commit. Since moves in HDFS are so fast, this is practically all or nothing. So we know reliable output works on HDFS, but what about in the cloud? We have a couple options here. First, we could just run HDFS on each Spark worker. So this is basically like replicating an on-prem Spark or Hadoop deployment in the cloud. But there's another option, which is we could use cloud-native storage. For example, Amazon's S3 storage system. So S3, Google Cloud Storage, Azure Blob Store, these systems are not really file systems. They have very different performance characteristics, and their API is closer to that of key value stores. So fortunately, it's not so hard to provide the file system API over object stores such as S3. There's a really common S3A file system, which is used to do this. This lets traditional Hadoop applications and Spark continue to work over cloud storage by using these adapters. So the question is, by using these, what do you give up in terms of like reliability and performance? So in the rest of this talk, I'm going to talk about why you should actually prefer cloud-native storage over HDFS in the cloud, the performance and reliability challenges that come when using these cloud storage systems for ETL, and what we're doing about this at Databricks. So to start off, let's compare HDFS and S3. When evaluating storage systems, you want to look at a couple dimensions. There's the total cost of ownership, SLA, performance, and consistency. So looking at cost first, there's kind of two parts of cost. There's the storage cost and the human cost. If you look at just the raw bytes, the cost of the raw bytes in S3 is like 4 times cheaper than HDFS on EBS. S3 is also fully managed, so contrast this to HDFS, which requires Hadoop engineers or vendor support. S3 is also fully elastic, so really you only pay for what you need. So overall, S3 is likely to be maybe 10 times cheaper than running HDFS in the cloud. For availability, Amazon claims 11 nines of durability, which is a lot, also 4 nines of availability. You're probably not going to achieve this running your own HDFS cluster unless you really have like a lot of operational expertise in this space. Then performance. This is a kind of interesting one. We break this into 2 parts, data plane throughput and control plane throughput. So in the data plane, HDFS offers higher per node throughput because you can sometimes get disk locality, like Spark tasks will run on the same node as the data is actually stored. On the other hand, S3 throughput will just scale to whatever your needs are. So it's likely you can get a better price per performance ratio here. So maybe it's a wash for the data plane, but on the control plane, S3 has some issues. Listing files is, of course, much slower. Also, renaming files requires a copy, and it's not atomic. So this means that renames of files get slower with the size of the file. And this really increases the window of failure during commit. If you recall, when we were talking about how Spark achieves reliable output, it does it by renaming files. If renaming files takes much longer, the chance of failure becomes much greater. Finally, there's consistency. HDFS provides strong consistency, which means that if you write a file, any reader is guaranteed to see those writes. Now, S3 only offers read after write consistency for some operations and eventual consistency for other ones, such as listing files, which turns out is pretty important for ETL. OK, so the conclusion here, I think, is like cloud storage is really preferred. It wins in terms of cost and SLA. You get a better price-performance ratio. It's also more reliable. However, it brings some challenges for ETL. There's lower metadata performance. You don't have atomic operations. And there's the eventual consistency issue. So to kind of make these issues more concrete, let's really look at an example in code. So here I'm taking an hourly metrics table and reading it to a data frame. I'm applying a filter to just look at 1 day's worth of data, applying some transforms, and then I'm writing that out to a daily summary directory in S3. So this is like a workload that you might want to prepare like the latest data for data analysts to look at. So from Spark's perspective, the job is executed in a couple of phases. First, you have to discover the input files. Then you apply data frame transforms. You write the output files. And if that succeeds, you commit. It turns out that cloud storage issues can actually affect every phase here. So let's look at these issues, and I'll break them down into terms of like reliability issues and performance issues. So the first thing you notice is that when you're discovering input files, you might actually miss some of them because of eventual consistency. So this is pretty bad because obviously if your input is wrong, the output of your job will also be wrong. Also, like during the job run, external readers might observe missing or partially written output files. You've noted in the example, we're writing the files in overwrite mode. The way Spark implements overwrite today is at the start of the job, we actually delete all the output files. Obviously, this means that if the job fails or someone is trying to read while the job is running, they're going to see no files or maybe some partially written files. Finally, there's the commit phase. So Spark does this by moving stage files to a final location. As we said before, this is going to be slow on cloud storage. There are some workarounds, such as there's this thing called, there's a replacement protocol called direct output committer that writes files directly to the final location, but this is going to leave partial output around on failures. Performance-wise, finding all the input files actually can take a long time if you have a very large partition table. So these tables can have maybe thousands of millions of files in them, and even if you're filtering by 1 day, Spark still has to find all of them. Finally, it's also not safe to enable Spark speculation against S3. So straggler tasks can actually slow down your job. So let's group these issues together. Some you can categorize as eventual consistency issues. Some fall under metadata performance. And finally, there's a kind of a bucket of issues I like to group under like lack of atomic commit. So these are issues that kind of affect HDFS as well, but they are much worse on cloud storage because of the metadata performance and kind of the lack of atomic moves. So we'd like to use cloud storage, but can we avoid having these trade-offs? And it turns out the answer is yes. You can leverage external services to provide additional guarantees on top of cloud storage. So let's look at how we can do this. First, we look at eventual consistency as an issue. So this is actually a problem for many cloud storage systems. Typically, you get some guarantees for a single object. Like if I create a new file, I'm pretty much guaranteed to be able to read that file back. However, if I'm like trying to list a directory, I might not necessarily see recently updated files. Again, to kind of like give you an idea of what this actually means in code, let's suppose we have this very simple example. We're creating 100 rows out of thin air using spark.range, and I'm just writing this using overwrite mode to some directory in S3. And after I do that, I run another command to read these files back out, and count the number of rows. So if the underlying storage system was strongly consistent, such as HDFS, I will always expect to see the answer is 100. But if not, then in principle, I could see a number of things. I could see a number that's less than 100. This means that some of the files that Spark wrote out just didn't show up. I could actually even see more than 100 if there was previous data because I'm overwriting it. This S3 can actually, if you delete a file, the file might still show up for a while. So this is kind of problematic. You could get duplicate data, you could get missing data, who knows. So this is eventual consistency is like such a problem. There are actually a number of solutions around this. There are some that are open source. There's like S3 Emperor from Netflix. There's S3 Guard in development from like a number of companies, I believe, like Hortonworks and Cloudera. And of course, there's like vendor implementations and services. So Amazon EMR has EMR-FS, which provides strong consistency. For Databricks side, we have DBFS, which serves a similar role. And all of these services kind of provide a strongly consistent secondary index. So the general idea here is that when Spark is listing files, not only do you list against S3, but you also make like another call to this secondary index service, and the client can read and reconcile the answers. Also, when Spark is writing files, of course, has to update the secondary index as well. OK, so eventual consistency is kind of a known issue. There's a number of ways to deal with it. Let's look at metadata performance now. So back to our example of our daily summary ETL job, you'll notice that the first step is we read that hourly metrics table, and then we're filtering down to 1 day. And you might think that because I'm filtering down to 1 day, how many files can there possibly be in 1 day? So it should be fast. But that's not necessarily true. So when Spark is planning the query, it actually lists all the files for that table before filtering. So this means that even if you're filtering on a partition file, it doesn't necessarily help because you still have to list all the files. This wasn't an issue for HDFS, but now that we're seeing more and more people using cloud, we decided to fix it. So this is actually kind of mostly fixed with scalable partition handling support in Spark 2.1. So this is work by Databricks and also community contributions. The general idea here is that we want to leverage the metadata catalog, that is the Hive metastore for Spark, to avoid expensive S3 lists when possible. That means that like when Spark is planning the query, it doesn't just directly list cloud storage to find all the files for a table. It first consults Hive metastore to prune these directories by the predicate, and then it only has to list the matching directories. This gives you much better scalability. So kind of here's a benchmark I took from our blog post. We're comparing Spark 2.1 with this scalable partition management enabled on top versus with it disabled. So you'll see that the time spent listing files, which is the red bar, scales with the actual amount of work Spark is doing in Spark 2.1. Whereas before, Spark has to pay this huge upfront cost of listing files over S3. OK, so that covers kind of metadata performance on the read side. But beyond read performance, there's the slowness of renames that can be an issue. We had a solution to this before. It was called direct output committer. It basically replaced like the default Hadoop MapReduce output committer. And the idea is you just don't bother staging files. Just write them directly to their destination. And when you commit, well, you don't need to do anything. They're already there. But what this is really doing is it's training reliable output for performance. And we actually ran into so many issues with this that we removed it in Spark 2.0. It's much better to work correctly than be fast and sometimes mess up. So this really brings us to the lack of atomic commit. So what does atomic commit mean? Let's look at our favorite example of writing 100 rows again. But this time, we consider 2 concurrent users, maybe running on different machines. One is trying to write 100 rows. Another is trying to read and count those rows. So if the write job was atomic, I would always expect either the previous number of rows or the next number of rows, which is 100. But on the other hand, if it's not atomic, which is the case today, you might get the previous value. You might get 0, 100, or you actually might get any value in between. And this is even assuming if you have strong consistency. This can happen even on HDFS, though, of course, the window of opportunity here is much smaller. So for for atomic commit, we want readers to see only committed data. That is, we want appends and overwrites for data to be all or nothing. And also, if a job fails, it should be like it never happened. It shouldn't really affect or corrupt my output data. And there's also like other issues that would be nice to fix. We'd like to have high performance. And we also like to have safe task speculation to cut like job tails. So we've been working on this thing we're calling the Databricks commit service, which can provide both high performance and robust output. The idea is pretty simple. We want to track the state of output files explicitly. And then we can make these output files atomically visible on commit. And you can also, because we're like doing this, we can also allow the files to be written out in place, kind of similar to direct output committer. And it's kind of tricky here, but we also managed to make this fully backwards compatible. We write kind of directory level markers so that it's compatible with Hive DDL operations, such as alter table, rename partitions, and a lot of other things like that. And to kind of give you an idea of how it kind of works under the hood, there's two components. First, on the read side, the reader consults with the commit service when listing files to kind of filter out uncommitted files. And when Spark is writing files, through the kind of commit protocol interface we discussed before, it informs the commit service of file creations, deletions, and also commits. So there's also some kind of garbage collection process to get rid of uncommitted files or files you deleted. So what this gets us is performance without trade-offs. The commit service provides both very high write performance and reliable atomic commit. So in a benchmark here, I'm showing a very simple benchmark of writing 1,000 files to Spark job. In a Spark job, 1,000 files is really not that unusual for an ETL workload. So here I'm comparing the default Hadoop commit protocol in Spark, in previous Spark versions versus a protocol that's using the commit service. So you'll see that the Hadoop commit protocol job actually took an order of magnitude longer to run, whereas the commit service was relatively fast. But what's more, if you actually break the time down for these jobs, actually when using the default commit protocol, the vast majority of the job time is spent just renaming files. It's not doing actual work. Whereas if you break it down for the job using commit service, you'll see that the commit time is nearly instant. And it's also, of course, atomic. So kind of in summary, if you're using cloud storage, there are going to be ETL issues. But you can get both consistency and atomicity without sacrificing performance. So we're really excited about this commit service. Right now it's in preview with selected customers, but we're hoping to enable the integration by default soon for Spark 2.1. So that's all I have. Thank you. You can try Spark 2.1 on Community Edition.
Thank you, Eric. We got 2 mics on either side of the aisle. If you have any questions, we've got about 11 minutes, so make most of it.
The Sampa team, they claim their put-based committer don't need renames either. How would you compare the two?
I think that would also work. It's a guarantee similar to HDFS, but you're not going to get true atomicity that way.
OK.
Go ahead, Doug.
Yeah, you mentioned it's going to be available in Spark. You're adding it to Spark 2.1 or 2.2. Does that mean it's going to be available in the open source Spark?
So unfortunately, since it has a service component, it's not very easy to release as open source.
Anybody else? Got a gentleman here.
So my question is when you add the atomic property, a relational database property into big data, so you don't think when the user read and when you make the auto commit, it will cause some kind of locking and blocking on a database, and then eventually it have some kind of performance when you run 1,000 batch processing job?
Mm-hmm. Yeah, so I think the question was whether this would have performance impact on readers, because in the traditional database world, when you have transaction protocols, you use locks, and you might cause contention. And the answer is here is we use kind of optimistic concurrency control, so it doesn't block readers.
Anybody else? If not, then give a big hand to Eric Liang, please. Thank you very much, Eric.